Okay, we're going to look at the output impedance of a cascode. Now the cascode is this nice little thing. You'll see this a lot with tail current sources and stuff at the bottom of op amps, and we'll discover why at the end of this. And of course, it's just one MOSFET stacked on top of the other one. How hard can it really be? We want to know what's the small signal resistance looking down the cascode, right? And as always, you start with your small signal model, and that's not hard to do. So the DC sources die, both the gates get grounded, and I've annotated all the gates and all the drains and all the sources very explicitly here. So this is source 2, this is source 2, drain 2, source 1, etc. Okay? And this is the unsimplified small signal model. We cut the circuit along our cask. We attach a test source of Vx and Ix. I've annotated the voltages here in red just to make it more clear. And the first thing that's immediately apparent is that VGS2, so this notation I have, when I put the 2 beneath the VGS, that's just VG2S2. So that's the voltage at gate 2 minus the voltage at source 2, right? And we'll notice that's 0 because they're both grounded, right? So since this is 0, this current source becomes an open circuit. So we'll draw the circuit again over here. Now we can look over here. And we'll notice that this current source is gone. That's why I didn't draw it, because it's drawing 0 current, so it's an open circuit. And we've still annotated VGS1, which is gate minus here. Now we'll notice that I annotated this node as V, right? I've just called it V because there's only 2 nodes in the circuit. There's the test voltage node with the test current coming out of it, and there's the voltage node. And since VGS starts at VG, it's really just minus V. Okay, great. Now we can simplify it a little bit more, or we can write it in a way that's maybe a little more clear what's going on. We want to think about it carefully before we jump in with KCL, because if we weren't thinking very hard, we could just KCL this node, KCL that node, do a huge amount of algebra, and then eventually find the answer, whereupon we'll likely make some kind of mistake. So we have to massage it a little bit and get the circuit drawn in a way that's comfortable. So when I see that my VGS becomes negative, what I like to do is I like to redraw it but change the direction of the arrow. So now we've got a third circuit here. And all 3 of these are equivalent. We're just writing it in a way that's a little more succinct. And I've also added this green box here. What this green box is the supernode box. So by supernode, we know anything that enters the box has to equal the current going out of the box. And now we're finally going to actually apply supernode and KCL. So when you do the supernode equation, you'll find that V, this voltage here, is simply Ix times RDS2. It must be, because the current out of the box has to be the current into the box. And we set the current into the box as just the test current. Great. So we do KCL at Vx, and we're going to say all the current is in, because we clearly have 2 currents going in already, so it's rather easy to derive, right? So here's our first current, GM1V, that's this one. We have Ix, of course, which is this one. And then we have V minus Vx over RDS1. So that's V minus Vx over RDS1, right? So now we have a KCL at that equation. Now these 2 equations are all we really need. We don't need any, the rest is all algebra, no more electrical engineering. So we do a little bit of algebra where we factor out the V, add on the other side. Then we substitute our supernode equation into V directly. Because remember, we want to get rid of V, because the answer should be Vx over Ix with everything else. So we factored the V immediately so that we could substitute it in. Great. Now, all I've done between this line and this line is substitute. So now you have Ix RDS2 GM1 plus 1 over RDS1 plus Ix equals Vx times 1 over RDS1. Great. We factor out the Ix again. We divide by Ix and we multiply by RDS1. And now we know the resistance of the cascode is Vx over Ix, which is just this thing. And then we multiply in the RDS1. And this is technically the resistance of a cascode. The one at the bottom doesn't come into effect. That the one at the bottom meaning the bottom MOSFET, M2. You'll notice there's no GM2 in this term. What matters is the transconductance of the top MOSFET. So it's GM1 times the product of the RDSs plus each individual RDS. And that makes sense because this is 1 over ohm times ohm, which is ohms plus ohms plus ohms. Anytime you add or subtract, you have to add unit to unit. You can't, add apples to oranges, at least not in one dimension. Now, there's a simplification we can make because this is still a little unwieldy, and it would be nice if we had a little, a nicer equation to deal with. So what we do down here is we say, hey, if GM times any RDS is much, much greater than 1, which is often the case, then we can do some further simplification. So I take our cascode, which is this expression. I factor out the RDS1. And we know that GMR is much, much greater than 1. So this term is all that matters in this parenthesis. So this is approximately equal to, as if this 1 just magically, zapped itself out of existence. So now you just have GM1, RDS1, RDS2, because the 1 is gone, plus RDS2. We do the same thing. We factor out the RDS2, and again, GM1, RDS1 this time is much greater than 1. And then you multiply in RDS2. Great, now you're done. This is the output impedance of a cascode. Very simple, succinct expression. GM1, RDS1, RDS2. And sure, it's a little involved and a little tricky, and the real trick is to use supernode, because if you write a KCL here and a KCL here, just brute force it, you will eventually arrive at this answer, but it's very time consuming, and you don't want to do that. And so you may be wondering, well, why do we care? Why not just use one MOSFET? Well, this number is huge because R is like, 10 or 100K times another 10 or 100K times like 0.1, maybe 100 millisiemens, right? So this number will be like thousands and thousands and thousands. And why do we want the number to be big? We want the number to be big because a current source in parallel with a very high resistance or an arbitrarily high resistance is just an ideal current source. So the more higher this number is, the more ideal this will look like a current source in small signal. So you want the number to be really, really large. If you didn't have a cascode, the output impedance, or the impedance looking down, would just be the RDS resistance, which isn't very good. Well, it can be good, application depending. The point is, you want this number to be really big, and it can be.